Okay, so our second speaker is, where are you, Isabella? Yes, okay. So Bella is a student who has been playing soccer on SSU's women's soccer team for years. So the research he did really is truly a reflection of what she loves. The two things she loves the most, physics and soccer. All right.
I'm not really sure. This doesn't quite go with my outfit, but should I just hold it? All right, well, this struggles. Okay, so hello everyone. My name is Isabella Amyx. Thank you for the kind introduction, Dr. Shi. And I did my research on the effectiveness of headgear in soccer. So as he said, I've been playing soccer here for the past 4 years and practically my whole life. So headgear is used to prevent concussions, and that is something that I am facing basically every day. Every time I go up for a header, any sort of challenge in the air, I'm thinking, oh, I hope I don't get a concussion. So that is what I wanted to focus my research on. So what is a concussion? A concussion is a type of traumatic brain injury. So basically, any big impact to the head that causes your brain to shake around in your skull and cause some sort of damage. And they're really dangerous if they're not, diagnosed right away or diagnosed in the right way. And they're super common, not just in soccer, but in any sport. So there's around 1.6 to 3.8 million concussions a year. So concussion happens anywhere between 50 and 90 Gs of force. So a G is an acceleration. It's basically a way of referring to an acceleration to gravity's force. So a G is gravitational force. So every force that we feel when we're walking around, that's a G of force. So it can happen anywhere between 50 and 90 Gs. So there's no cure for concussions, but the prevention, these headbands, are super controversial. So here you can see, there's a little picture of me playing soccer. So there's two main brands. There's the Full 90 Premier and the Storelli Exo Shield headband. And the makers claim to reduce the force of the head by 50%. And so I saw this statistic and I was like, 50%? We should all be wearing these, But no one is. So if that's the case, then we should be advertising this. Everyone should be wearing these, protect your brain. And if it's not, then that should be advertised as well. So a way of thinking of how these headbands work is like a wine glass. So if you drop a wine glass on this carpet, you'll probably find it won't shatter. But if you drop it on a hardwood floor, it'll most likely shatter. So it's got that little cushion. And that's what these headbands are trying to do. They're trying to cushion your impact. So how would I test this? I basically had to create a controlled environment, which basically means I can create an environment where I'm creating the same impact over and over again the exact same way. So if I am going to set a ball up and try to kick it at the wall, I'm probably not going to hit it at the same speed to the same spot every single time. So I had to create an environment where that is the case. And from there, I can change multiple factors such as the type of headband, different brands, the speed, the direction, the pressure of the ball, and the area of impact, so where you get hit on the head. And so in my presentation, I'm going to talk about the first two here, the type of the headband and the direction. So how do I make this controlled environment? Obviously, like I said, I'm not going to be able to kick a ball or throw one the same speed as a soccer player in the same direction. So basically, what I did is I used a weighted ball and created a system that has equal momentum as you would experience in a game. So if you can see here, I'm not good with this pointer, but momentum is mass times velocity. So if a mass of this soccer ball, regular soccer ball, is 0.43 kilograms and it moves at around 25 meters per second, that's about an average, I can create another system right here and use a higher weighted ball and the velocity will go down. So you can see by this messy math here. I used a 3 kilogram ball here and I can calculate how fast I need it to be moving to create this exact same system. So the way I can reproduce this the same way every time is using a pendulum system, because what's more consistent than gravity? Gravity is always going to be the same. So you can see by this equation here, I know the final velocity I want it to be at the bottom of the swing, right? So all I need to find is how high do I need to drop it so I get to that velocity. So by these calculations, you can see I need to drop it about 2 feet up. So here you can see my setup in the lab. I basically got my weighted ball right here and the Pasco 2-axis force platform. And so you can see here's a bigger image of what it looks like. The Pasco 2-axis force platform basically has 4 different force sensors on it, one on each corner where those dots are. I don't know, people in the back, you might not be able to see it, but there's 4 different points right here. And so the way that works is, let's say these are used a lot for kinesiology majors. If I want to see how much force is going in when I'm jumping, I can see how much force is going into the ground and how much is going away, a parallel and a perpendicular force. And then I use Pasco Capstone as my system and a Pasco AirLink as my data acquisition. And the aim for this was basically so I could, use it outdoor if I needed to. So it's kind of like a wireless data acquisition. So here's a little video. It'll show you basically what I did. And I was lucky enough to find this little black rolling table that was the exact height I needed to drop it and get that speed. You know, what are the odds? And so you'll see me pull out that rolling table so I'm not pushing on the ball. Nothing's changing. I'm pulling it out so it's going from 0 to get to that full swing. And I don't know if there's sound on this, but it makes a really loud, like, oh good. You won't hear it. But it makes a really loud hit at the bottom, and that was really, you know, it was hard to hear all day long. Oh, you do hear it. So that's basically that impact, that loud noise that you maybe heard. That's the impact that I'm measuring. And here you can see another slow motion video. And what these things are here, these are lead bricks. Basically what I did is I put it up against the wall, put some lead bricks there so it wouldn't move, and then I swung and hit the ball. How do I do this? There you go. Probably didn't hear it in the back, but it was a loud noise. And then you see here there's something, you might not see it in the back, but there's a little cushion right in front. And what that is one of the headbands. So basically what I did is I cut the headbands, which is hard for me to do because they're very expensive. But I cut the headbands right in half and I taped them over the top left corner, which is what I'm aiming at. Ryan, can you hear me okay back there? Yes. Okay, good. Okay, so what does this data look like? So basically this data right here is 5 different swings without the headband. Okay, so each of these peaks is when I drop it, I catch the ball, I put it back up, and I drop it again. So you see an average about 1,200 newtons of force. It's kind of a lot. And right here in these 2 little images here, these are basically a zoomed in photo of right here, right at the bottom of the first peak. And these photos are just to show you how fast these impacts are happening. So you're getting, let's say in this peak, I know you cannot see the numbers, but this peak right here, this first one, is around 1,150 newtons of force. So you're getting almost 1,200 newtons of force in 0.03 seconds. That's just a lot of force in a short amount of time. So here's another data of the impacts with the full 90 headband. So you can see it goes down a little bit, and it's around 960 newtons of force. And right here, this little error here is actually, I dropped it and one of the lead bricks fell, so I had to walk over and fix it. And so that's what that little divot is right there. And then lastly, here's the impact with the Storelli ExoShield headband, which again went further down. And so, like I said before, when those lead bricks were falling, I had to readjust and end up doing just 2 rounds of 3 drops. And so that's where you get the 2 different colors. The red one is run 1, and the baby blue one is run 2. So like I said, it went down 890 newtons of force. So altogether, you can see that definitely the force decreased a little bit using the headbands. So after calculating the data, I found that the headband, using the full 90 headband, the force decreased by 20%, and the Storelli ExoShield, the force decreased by 26%. So not quite 50%, but that's something, right? And so relating it back to concussions, this system here creates almost 50 G's of force. So that's where you're entering that range of, okay, you might get a concussion, you know? And these ones are around 30 to 35 G's of force. So again, like I said, not 50%, but you're getting there. And what this data tells me is that, okay, maybe they're not what they seem, but that's definitely just something that we could keep looking into. So the last bit of research I did is I actually changed the direction of the impact on the sensor. So you can see these wooden blocks here. It's at an angle of 20 degrees, and I basically did the same thing. I posted up that sensor with a lead brick, and I ran it the exact same way. And this was basically just to see, okay, I have a 2D force sensor, let's use it. Up until this point, all I had been measuring is a straight impact, straight to your head, and that's not really game realistic. You know, you're going to get hit from all angles, all areas of your head. So if you see in this one, I know you cannot see the data axis, but this is around 900 newtons of force, and this is the normal force. So this is the force going right into your head. So compared to 1200, that went down a significant amount. And right here you can see it's around 150 newtons of force going laterally, parallel to that force sensor. So obviously from this data we can see that when you get hit at an angle, the force going into your head decreases, because all we care about is that force going into the sensor. You know, you want to know how much your head is actually taking versus, you know, going across your head. So obviously it did decrease a little bit, and this was something that I would really like to go into, or if someone continued my research could continue looking at. So here you can see future work. I would definitely keep looking into that 2D forces. So I'd basically look at the different angles, what angles have least amount of force, which have most, and then add those headbands and see if that helped even further. Then I would adjust things like the speed, the pressure of the ball, and the area of impact. The pressure of the ball one is really interesting, and that's one I thought of at the beginning, is if you're playing in Wisconsin, freezing cold, the ball is going to be a different pressure than if you're playing in Southern California and San Diego. So it's interesting to see how would that temperature change the pressure of the ball and therefore change the forces to your head. And lastly, I would eliminate sources of error. So this was a big thing that was bothering me all throughout my research. The little things that could have been a little cleaner and maybe clean my data up a little bit and get a little bit better data. So adjusting the ball drop. Basically, if you saw in that video, you may not have seen it, but when I pulled the ball up, there was a little ledge on that black table that caused the ball to kind of wobble into the sensor. So I might be hitting the sensor on a forward swing or a back swing. That would change a little bit of the data. And then mounting the sensor would make a big difference. So the walls were a little too thin to mount the sensor. It's a really heavy sensor. So the walls were a little too thin to mount. So I had to use those lead bricks. And those lead bricks were a big source of little errors or little things that I would have to adjust and fix every single time. So I think mounting that sensor would have been a big help. And lastly, I'd like to thank Dr. Shi again for helping me out and being my advisor, and Ryan Brown for all the help with collecting all the materials, and obviously all my classmates, and thank you all for coming. Oh, any questions? Yes.
Yeah, so based on your research, do you recommend that kids start wearing them? Or do you wear one?
It's a great question. I was waiting for that question. So my mom here today used to make me wear them in high school a lot. So she heard about these headbands. She's like, you need to wear them. So I actually wore them in high school. And when I heard the controversies of, oh, I don't know, they might not do anything, I stopped wearing them, and I don't wear them right now. I do see girls wearing them still. And after my research today, I would say I wouldn't necessarily jump to wearing them right away, but I think there's definitely a lot looking forward into it, and there's a lot of things that we could do to improve the headbands and soon make them something that maybe everyone should be wearing.
What is the headbands? What's the material that they're actually made of? Was it the same material for both?
So the Storelli ExoShield was more of like a memory foam kind of material, like those nice pillows. And the full 90 was a little more, it felt more of like a cheaper material. There's nothing in them. I remember I was talking to Scott, who just walked out, but he was asking if there's a metal rod in there, maybe that would be a better way of distributing the force. But there's actually nothing in there. All they did was put together some cushion, different kinds of materials, and put it into a headband.
Have you thought about sending this project of yours to the company?
I have not, but I definitely think if I cleaned up some of the possible errors, that would be something that we could do, definitely.
Is there any data on concussions with kids using the headbands? Did you know if there's any?
What I've heard is that if you're going to get concussion, there's a lot of things that cannot help you. So like a big part of my research that I did not cover is head-to-head impact. So that is a big source of concussions. Getting hit by the ball is one thing, but hitting your head against someone else's head, that's a much bigger impact. So most likely if you go head-to-head and you're getting hit with that amount of force, you're probably going to get a concussion without the help of the headband. But I've heard the headband can definitely help with just ball-to-head kind of impact.
Let's thank Bella again.